Hello, my name is Alex. I work in QuickField support team. Today we will talk about new features of QuickField 5.9. The new features are temperature-dependent electric conductivity in several problems and import of DC-biased magnetic permeability. Let's start with the second one, import of DC-biased magnetic permeability. This feature was introduced in QuickField 5.8. It was possible to import magnetic state from DC to DC magnetic problem. That is useful when you have several sources and need to calculate fluxes separately. For example, in the speaker there is a permanent magnet and the coil. We should take into account the saturation caused by the permanent magnet, and at the same time we need to calculate the flux created solely by the coil in order to calculate the coil inductance. The total flux is a sum of flux created by permanent magnet and the flux by the coil. And we need to separate these fluxes. The coil inductance is the flux created by the coil divided by the current in the coil. With DC to DC import, it is possible to divide the problems. First, we calculate the saturation level caused by the magnet, and in the second problem we switch off the magnet and calculate the flux from the coil. This is QuickField. This is the first DC magnetic problem to calculate the saturation level. I have air, coil, magnet, and the coercive force of the magnet is specified. And I have the body of the loudspeaker. The body is made of sound magnetic material. The BH curve is specified for the body. The result of the initial problem is magnetic field distribution. I can adjust the field picture. You can see the flux density level is relatively high. And I can switch on the magnetic permeability picture. I will adjust it a little. Here you can see that some parts of the magnetic body are saturated and some parts are not. We should take into account this when calculating the inductance of the coil. This is my second DC problem. It is linked with my initial problem. I import magnetic state from one problem to another. In my second problem, I switch off the magnet. There is only the coil to create magnetic field. The result is on your screen. This is the field lines and magnetic flux density distribution created by the coil. You can see the flux density level is very low. We have very small value of the current in the coil. At the same time, the magnetic permeability is the same as my initial problem with permanent magnet. This way I can calculate the inductance with respect of the saturation of the core. In QuickField 5.9, this feature is extended to AC magnetic analysis. This feature is useful when you simulate DC AC devices such as electrical machines with permanent magnets, actuators with permanent magnets, reactors. Let's take a look at the example. This is the filter reactor. The purpose of this device is to smooth the current fluctuations. From thyristor power source, I get DC voltage with some fluctuations. I would like to smooth fluctuations. I place the reactor at the output and hope that its inductance will lessen the fluctuations level. Now, what the inductance value is, I cannot calculate it with DC, as it is not the DC current inductance that I need to know. I cannot calculate it with AC, as the reactor could be saturated by the DC current. What I do now, I calculate saturation level in DC, and then I import the magnetic state to AC magnetics problem. Here is my QuickField problem. This is the magnetic state problem. I have the air, the core, it's the ferromagnetic material, the BH curve is specified for the core, and I have the winding. In DC problem, I specify the DC current as a source in the winding. The result is magnetic field distribution, and I am interested in permeability distribution. You can see that some parts of the coil are saturated and some other parts are not saturated. Now, in my AC magnetic problem, I specify the frequency. This is the base frequency of my noise signal, 300 Hz. And I add the link to the magnetic state problem. In the model, I do not specify the permeability as it is imported from the DC magnetic problem. In the winding, I specify the current, the AC current value. And the result is magnetic field distribution. You can see the flux density level is very low. At the same time, the permeability is the same as in DC magnetic problem. Now I can calculate the inductance. This is the dynamic inductance with respect to saturation level caused by the DC current. In fact, the fluctuation, the noise, signal consists of an infinite number of frequencies. We found inductance at the base frequency only. And what about others? In QuickField kit, you can find label mover utility for parametric calculations. With its help, I can easily find inductance at any number of frequencies. Here is the label mover. The work with label mover is very simple. First, you should choose the base problem. Then you should choose the values to measure. I will measure the flux linked with my winding. And you should specify the parameter to change. I will change the frequency. Now I have the base frequency of 300 Hz. I will increase it by 300 Hz more. And I will repeat this step 10 times. Now I am ready for my transient analysis. The analysis of dynamic inductance at different frequencies. I press Get Result button. A set of QuickField problems is generated. For each problem, the specific frequency is specified, and the flux linkage is calculated for the windings. We have a poll question now, and then we will continue with other features of QuickField 5.9.